Hello everyone, welcome back to another video for the series. I'm Inokyu and today I brought a geometric problem from USAMO. So without further ado, let's start. Given circles omega sub 1 and omega sub 2 intersecting at points, let be a true intersecting at U and intersecting points R and S. Prove that if P, Q, R, S lie on a circle, so if quadrilateral PQRS is cyclic, then the center of the circle lies on XY. So we have two circles right now. What is that? One here, and that's so bad. I think I can do it. I should have just one last time. Yay! And something bigger. Not bad. I don't like how they don't intersect, but so this one is omega sub 1 here. I'll just name the center as omega because I think that might look more simple. So we have x and y. Okay, and let's arbitrarily draw a line. So we have P and Q, and ideally we want the center to be around here. I don't think the drawing. Wait. The center should be around here, so maybe something like this. Does it work? Oh yes, actually I think this is a great circle. So maybe something like oh, I got it. So if I tilt the pen, then my drawings are so tilted. That is a valuable lesson. Yeah, so I think I should be drawing something like this, but something better. So I mean, not that bad. Oh. Why can't I draw a straight line? Believe it or not, I actually draw way better on paper. What? Yes. That's This one feels good. Yay! So we have PQ, R, and S. Notice that, and the center should be, yes, okay. So let this one be omega sub 3. Notice that, so first one, let's look at, oops. Let's look at, wait, I think I should use highlighter instead. This one, and wait, I think I can just use pen. I think that will be better. So the first one that we are going to look at now is this one and this whole thing. So we have omega sub 1. So looking at omega sub 2 and omega sub 3, the radical axis for these two triangles is PQ. And because we know that by construction, omega sub 1, PQ are collinear, let's write an equation using the PowerPoint in terms of omega sub 1. So the power of omega sub 1, the point omega sub 1, from these two circles are the same. So writing, we have omega sub 1, omega sub 3 squared, minus, let r sub 3 be like the radius of omega sub 3. Squared equals omega sub 1, omega sub 2 squared, minus r sub 2 squared. And now let's look at these two. This one and this one. So by looking at them, we have for omega sub 1 and omega sub 3, RS is the radical axis, and by construction, our W sub 2 lies on the line RS. So we could do the same thing, write an equation based on the point, the W sub 2. So the power of W sub 2 from omega sub 3 is omega sub 2 omega sub 3 squared minus r squared, and this is equal to 1 omega sub 2 squared minus r sub 1 squared. Now let's organize what we know. So using these two equations, subtracting it, we know that equals squared. And wait, these two cancels. Equals, so these two cancels, these two cancels, so negative r. Plus, so we have what? minus r sub 2 squared. Okay, so we know that this is the power of r sub 1 r sub 3 minus w sub 3. Wait, I forgot how to write the notation. But I think it's quite universal, and if my memory serves me right. Oh wait, but actually there's no like set symbol for this, so I'll just write it in a way that sounds most plausible and like how I remember. So the power of, is it omega sub 1? Whoa, no. Omega sub 1, omega sub 3, and this is equal to omega 2. Is this right? Let's double check. So from omega sub 3, it is the power of omega sub 3. And that is right. And yes, so we know that the power of omega sub 3 from omega sub 1 and omega sub 2 are the same. That means it lies on the radical axis, and radical axis is the traces of all the points that has the same power from the two circles, and like it is if and only if condition. And also we know that the radical axis is a straight line like this. And thus we should have it here because we know that it's the same. And that completes our proof. Omega sub 3. I think this problem was quite meaningful to me because it's been a while since I tried a problem related to I think I did something related to radical axis when I was proving, when I was proving Bryanschan's theorem here in this series. You could check it. I think I forgot the date, but it's there somewhere. But like it's been a while since when I've solved a problem that is related to radical axis, and yes, I think it was a great review for me and hopefully to everyone. So I think the kick here is to notice that these two are also the radical axis, not only the red one here. Then thank you so much for watching this video. Tomorrow I'll come back with another very fun and interesting problem. And thank you and see you tomorrow. Bye.